Okay, we've had some good examples. People are picking up the small p. People are picking up the small probability, which is great. The things that people are missing are to say what exactly you're counting. So yes, there might be a small probability of an accident outside, but what are you counting? I want you to say something like, well, there's a large number of days in the year, 365, and there's a small probability of an accident on any days. So how many total accidents do we get in the year? What people are missing, what people are doing right, first of all, is the small, we've got NP, haven't we? We've got N times P, yeah? People are very clear on this small probability, and there's lots of really good examples. It's the N that's missing. People are not saying exactly what they're counting. People are not saying, right, we've got a small probability of winning a jackpot. Yes, but what you're counting, what I want is something like number of jackpots in a given day or number of jackpots in a given week if you're doing slot machines. People were talking about fruit, somebody talked about fruit at the market, a pack and save. Yes, there's a small probability of having a piece of fruit that's bad, but what the Poisson distribution is the number of bad pieces of fruit in a case. Because you've got, say, 600 bananas in there, and each one's got a small probability of being rotten. But by and large, the examples I got were quite good. Number of complaints at Burger King. I like that one. You serve a large number of customers, and each one's got a small probability of being some kind of nutcase who'll complain. So there you go. About 3 a day, which I thought was a bit high.
Number of near misses by the bus. Right.
Indeed. We've got people who keep chickens, and they've got small probabilities of getting, what was it, a small egg?
A mini egg.
A mini egg, yeah? So you've got 1,000 eggs, let's say, in a week. But you see, in each case, we've got, what are you counting? You're counting the number of mini eggs, the number of complaints, the number of, what else, what were the other examples that we came up with? Number of, yeah, okay, here's another one, the bus being earlier than scheduled. Yes, that's a small probability, but what exactly are you counting? You've got to have an N here to balance it out. So you might say the number of times that the bus came early in this year, which will be a Poisson with a particular distribution. So there's some good examples there.
The number of fish lost out of the machine within 3 hours.
Yeah, that's it, because you've got, so the comment was you've got a fish machine that processes a fish and it fails in some way. It's processing 10,000 fish.
So the N is a parameter or something?
No, it's not. The comment was N is a parameter. It's not. Lambda's the parameter, but it's because you don't care what the N and the P separately are. You only care about the product. That's why you keep the lambda as the product, but the N and the P don't. They just need to be in the back of your mind. And as I showed with the raindrops example, depending on how big the storm you consider, the bigger the storm, the larger N, but the smaller P. So they don't even have to be real things. It crops up all over the place, the Poisson distribution. Number of times you get a double-headed coin or something like that. Okay, so let's have a look at an example, see if I can find one on AUT Online. Actually, I'll use Google here. Football League goal results. Let's just have a look at that. See if I can find a database for it. World Cup will do. Let's have a look at that. Let's try that. World Cup records. No, it's not here. It's not the one I wanted. What I'm looking for is a league table of how many goals that were scored, and I'm struggling because I'm googling the wrong term.
Or by team or by?
By team, yeah. Soccer. Soccer league results. Here we go. Here we go. Ah, this is what I want to see. But I need the actual goals scored. I had it this morning. How do I get the actual goals scored on this?
That's blank anyway. Here and they haven't started yet.
Oh yeah, that's probably a good point. Here we are. Right, here we go. Here we go. Look. Let's forget the fact that it's a game of two sides, and we'll just look at these. We'll just look at these scores here. Now, why do I think that the number of goals scored by a team will be a poisson? Well, it's because you've got a large number of minutes in the game and a small probability of scoring the number of goals, scoring a goal in any one of those minutes. So let's just work with this here. What's the largest number? 3 there, isn't it? Well, actually, let's go down here and have a 4 as well. So we'll go down to there.
Is this how they figure out when you're making bets?
Yes.
How 2 to 1 or 20 to 1 and all that kind of stuff.
Are you seeing what I'm doing? I'm going down there. That was a 3-0. This is a 2-1. 2-0.
0-2.
0-2.
1-3.
1-3.
2-2. 1-2.
1-2.
1-1. 1-2.
4-0.
4-0.
And we'll do the last one 2-0. So we've got this little table here. Let me put it into R and see what happens. So what I'm doing here, hopefully, is showing you what I want for what kind of thing it looks good in a project, in a portfolio. So I'll say goals becomes
6-6-9-2-1.
no, I want the actual ones. I want the actual ones.
So 0, 7.
Here we go. 0, 2, 3, 0. See, I'm just copying these guys here. 2, 1, 2, 0, 0, 2, 1, 3, 2, 2, 1, 2, 1, 1, 1, 2, 4, 0. Ooh, that looks like a 12. There it is. An average of 1.416667 goals, which looks about right, doesn't it? Just looking at the numbers, some zeros, some 2s, some 3s. Now, that's number of goals, but in your head, I want you to be thinking that's number of complaints, that's number of rotten pieces of fruit, that's the number of crashes, that's the number of eggs, that's the number of fish, whatever. It's goals as well, but I'm wanting to tell you the great generality and abstract nature of this. It's applicable all over the place. Six, 6, 9, 2, 1. Yes! Look, we've got it right. Normally I make a mistake here.
Now you got to throw in minutes.
Well, I could do. Let's have a look at a table. There we go. So again, how many times did you get 0 scored? 1, 2, 3, 4. If I was being a bit cleverer for a portfolio, I would expect you to do this. To count the total number of goals scored in the whole match. 2, 3, 3, 2, 2, 4, 4, 3, 2, 3, 4, 2. Okay? No score draws here. Maybe they've brightened up on, because when I was a lad it was nearly all 0-0. Scottish Football Premier League and all that. Queen of the South 0, Kilmarnock 0. Alright, but we'll just take it per side. I just want you to pick up the fact that I'm changing how I'm analysing. There's no right ways to analyse this. I'm analysing this, the number of goals scored by the playing teams, but I'm not organising it by matches. I'll do it by matches later and see what happens. But for the moment, we'll just use these numbers. So we've got our table here. What's the total number of games, total number of players that we've got? We've got 12, we've got 10, 12, we've got 24 altogether, haven't we? So what I'm going to do now is I'm going to use the Poisson distribution to see how many of those 24 sides are going to score each number of goals. So I'm going to use the Poisson distribution to figure out prob of 0 goals, prob of 1 goal, all the way down to 4 goals. Okay? So I'm just going to use the Poisson distribution to do that, using what was it? What was the number that I got for the average number? 1.4 something, was it?
1.47.
1.417. 17. So all I've done is taken that value there and just written it out. Just written the density function down, the probability mass function down. Now I can't be bothered with that. I'm just going to use d plus. What's the probability of having no goals? Quarter of the time we get no goals. Are you following this? D plus just gives me that formula there, but just done in an intelligent way. And I want the probability of having no goals. Lambda equals 1. So, as an example of a null hypothesis, you could say you're playing really badly, guys, because you scored no goals. The response is, your null hypothesis is, we're scoring as many goals as anybody else. The definition of p-value is the probability, if the null is true, of observing the observation, which is 0 goals, or one more extreme, which can't happen. You can't have negative goals, however bad you are, even if you are Graham Taylor. And so the p-value for that is 24%. Not significant. So it's all very well for the manager to say you've scored no goals, you suck. Applying statistical reasoning says there's no evidence, because it happens 0 all the time anyway. Let's have a look at 1. We could just have, well, let me just carry on. 1. I'll just do a few more. I'll just do a few, and then I'll. So these are the probabilities of scoring 0 goals, 1, 2, 3 goals. See how the probability is falling off quickly now? So of course what I'm going to do is whack them all together. 24%, you see it's matching. 34, 24, 11 and 4%. And we can ignore the others. We can ignore the others. So those are the probabilities. These will not add up to 1 because there's a finite probability that you've got 5, 6, 7, 8, 9. Let's see what the probability is. It's not going to be very high. You can see that the probabilities are falling off and it's down to 4% now. And the next one might be 2%. So you're adding teenier and tinier, teeny, tiny, teeny. You're out in the tail end of that distribution. So we're going to get something like 0.98. Oh. Okay. So what I'm going to do now, these, I'm going to rephrase what I've got here. I'm going to talk about these guys being observed. This is the observations. And as I keep on saying, and this is true for all branches of science, science is precisely a comparison of observation with expectation. And as you get cleverer and more sophisticated and do more and more brilliant science, and as you come along to win your Nobel Prizes, what happens is three things. First of all, your observations get better and better and better because you're looking cleverer. Secondly, your expectations get better and better because you've got more sophisticated theory to bring to bear. And thirdly, your comparison between observation and expectation gets better because you're doing this course. So how do we turn these probabilities into an expectation? Well, I'll just multiply it by 24 because I've got 24 data points. 5.8, 8.2, 5.84, 2.75 and 0.97. So out of my results, let's just go back to the data. If I can find it. Out of this data set here, we've got 24 observations. I could have carried on. We've got 24 observations. I'm expecting 6 of them, it's 5.8 of them, to have 0. And we've actually got 6. How many teams do I expect to score 1 goal? 8.2. What do I get? 6. What's the next one? Oh, it's gone. 5.8, we've got 9. 2.7 against 2, and I'll come back to this one in a minute. So sometimes the observation and the expectation are quite close, and sometimes they're a little bit further away. Is it consistent with it being a Poisson distribution? Are these numbers here consistent with that or not? Well, let's have a look at what actual Poisson distributions look like. That's what my team's goal scores look like if it's Poisson. Of course, it's random, because it's R random for Poisson distribution. Where does that come from? Estimated it from the data. Where does that come from? Because I've got 12 matches and 24 scores. Different each time. I'll make a table of it. This is my imaginary league. Doesn't look too different from what I've got. What did I get? 6, 6, 9, 2, 1, 5, 8. Oh, it's not too bad. We're seeing a lot of scatter. Let's just look at the 1. 8, 9, 10, 7. We're seeing scatter. Are these observations here consistent with that expectation there? That's the question. They don't look too bad, do they? So that's a hit. If they are consistent, I'll show you in the next few minutes, I'll show you a formal way to compare observations with expectations. But you can see it's well within the ballpark. No pun intended. How do we formalise that? Well, the first thing we need to do is to sort out these probabilities, because these, let me go back to my probabilities. They don't add up to 1, or they don't add up to 24. Oh, that's multiplied by 24, isn't it? These probabilities don't add up to 1. So I'm going to force that one to be I'm going to change that one to include all the tail probabilities there. Okay? So let's have a look at these guys here. That's the first 3. And so what I'm going to do is I'm going to increase that one to make the probabilities add up to exactly 1. Do you see what I'm going to do? Because it only added up to 97%, was it? 98. So if I subtract 0 to 3, this is now the probability of 4 goals or more. Okay? So my probs are now tell you what I'm doing here. I'm going to combine the probabilities of having 0, 1, 2, 3 goals with my fill-up value, which was 0.055, which is 4 or more. Going too quickly? All right. So those are my these should add up to 1. Why? Because I forced it to add up to 1 by adding that guy there, which was 1 minus all the others. All right. So let's just check. I'll say probs. Oops, becomes that. Probs is that. Sum of probs should be equal to 1. Give me a break. Now I've got the number of that's my expected number of games. So I'm expecting 5.8 games. You see how my expectation can be a decimal. It can be between 5 and, it's like having 2.4 kids. Everybody's got an integer number of children, but some have got 3, some have got 2, some have got none, some have got 5. So we've got an average number. 0, 1, 2, 3, 4. How do I compare them? How do I compare observations with expectations?